All right, welcome. In this video, we're going to go through Lewis dot structures and some exceptions to the octet rule. So the octet rule is the rule that tells us that typically, so we're going to put this rule in quotes because it's not always followed. That there's, but most often atoms will tend to form bonds that will result in each atom having 8 electrons around it. Notable exception being that hydrogen and helium up there in that first row will tend to have 2 electrons around them because all they have is a 1s orbital. But basically what happens is they'll end up forming bonds that you have 8 electrons surrounding each atom in your Lewis dot structure. We will notice though that there are some exceptions to the octet rule. And the 3 exceptions for you to be aware of is that sometimes you end up with molecules with an odd number of electrons. You can have molecules where some of the atoms have less than an octet. And then the most common one we will see is when you have molecules that have expanded octets. So you have some atoms within the structure with more than 8 electrons around them. Let's look at the odd number of electrons to begin with. These are relatively rare, usually fairly reactive, but they do exist in nature. And what happens is, like, let's say NO, nitrogen monoxide, if you add up the number of electrons, nitrogen has 5, oxygen has 6, you have only 11 electrons total to deal with. So it's going to be impossible to give every atom an octet if you have an odd number of electrons. So what you do when you are drawing a structure for a substance such as this, you still just kind of do your best when you are following the steps for doing a Lewis dot structure, and you just get as close to an octet as possible. So notice in this final structure, we end up with like 7 electrons around one of the atoms instead of 8. So you'll end up with 7 instead of 8 on one of your atoms. That's just kind of the best that you can do. So just do your best. Okay, so this will happen sometimes. Another possibility is that some molecules will form where one of the atoms will end up with fewer than 8 electrons. And this mainly happens with boron and beryllium. It happens with atoms that are to the left of carbon on the periodic table. So we'll notice that boron starts out with 3 valence electrons, and it will end up just making 3 bonds. So when you have boron trifluoride, the structure looks like this right here. You might look at that and say, well, according to our steps for doing the Lewis dot structure, shouldn't fluorine just be sharing its electrons with boron? Like, why doesn't fluorine do that and just give boron an octet? And it has to do with the fact that these elements to the left of carbon on the periodic table have relatively, low electronegativity values. They've got, only 5 protons, got a relatively weak effective nuclear charge. So boron's nucleus is not going to be, strong enough to kind of pull those electrons away from fluorine, which remember is a really electronegative element. So boron's happy just having 6 electrons around it. Beryllium starts out with 2 valence electrons, and it's happy just forming, 2 bonds, and that's it. So these elements to the left of carbon will be happy with less than an octet. Mainly it's boron and beryllium where you will see this. More than 8 electrons, this is the most common exception that you will run into. And we know this happens in nature. So for example, phosphorus pentafluoride is something that occurs in nature. And the only way that this could work is if the phosphorus has 10 electrons around it. And we'll learn some shapes that are associated with these structures as well. So we'll learn some new shapes in this class that you didn't learn in regular chemistry due to these expanded octets here. And this only happens with elements in the 3rd row or below. And that means we're talking like on the periodic table, 3rd row, right? And if we think about why, well, we know the elements in the 1st row, hydrogen and helium, only have 1 shell. So all they have is a 1s. That's why they can only fit 2 electrons. 2nd shell has 2s and 2p, so it can hold 8 electrons. When you get to the 3rd shell, though, and below, we actually have d orbitals there as well. So there are these kind of empty d orbitals there that gives us some extra room for electrons to go into. And there's some kind of debate now about kind of what role these d orbitals are really playing. But if we're noticing the 3rd row or below can have an expanded octet, some ideas as to why this might be is due to the relatively larger size. So as you go down the periodic table, the atoms get bigger, so they've got kind of room for more atoms to bond to them. And then also these empty d orbitals maybe give you some room to fit more than 8 electrons in, surrounding that atom. Okay. So here's a sample problem with an expanded octet. So the way that we find the Lewis dot structure, we'll follow the same exact steps that we did otherwise. So step 1 is we're going to add up the number of valence electrons. So xenon has 8. And then you've got 7, we've got 4 fluorine atoms, each are 7. So you've got 8 plus 28, we've got 36 electrons. Super important to do this first step and count electrons. You put the least electronegative element in the middle, and then you connect everything else to it with single bonds. So step 1, count the electrons. Step 2, put the least electronegative in the middle and connect everything with single bonds. Step 3, you're going to give your outer atoms an octet. And then you are going to stop and count and figure out how many electrons you have left over. So we had 36 electrons, and so far we've used up 8 times 4. We've used up 32 electrons. So I've got 4 electrons left over. And this step in the process, I can't remember if it's step 3 or 4, but we're told to put these extra electrons on the central atom, even if doing so results in more than an octet. So that's what we do here. So we put those 4 extra electrons on the xenon. And it doesn't matter, where you put them. You can put them, next to each other or on opposite sides. What I wouldn't do, though, is we shouldn't draw them as being 4 separate electrons, because we know that electrons will exist in orbitals. So those 2 extra unpaired electrons they'll kind of exist in pairs. So put the dots next to each other, if that makes sense. And that's your structure for xenon tetrafluoride. So we'll go over a few more examples here. So like NO2, and these are ones that if you haven't tried them yet, you should pause the video and try them first, and then you can come back and check your work. So NO2, we've got a 5 and 2 oxygens, or 2 6s, so we've got 12, 17, we'll check my mental math here. So we've got an odd number of electrons. Okay, so I'm going to put the least electronegative element in the middle, that's nitrogen. Then I'm going to connect everything with single bonds. Then I'm going to give my outer atoms an octet. And then I'm going to stop and count and see how much I have left over. So I had 17. I've used up 16. I've got 1 left over. So I'm going to put 1 right here in the middle. And now I'm going to stop and check for an octet. So notice how each oxygen has an octet. They're happy. My nitrogen only has 5 electrons around it. So I'm not going to be able to give it 8, but I can make it better than 5 though, right? So I can take a pair over here and force that oxygen to form a double bond. So now if I stop and count, this oxygen still has an octet, this one still has an octet, and now my nitrogen has 2, 4, 6, 7. It's got 7 electrons, which is much better than 5. So that's my correct structure for NO2. And it turns out this is actually something called a resonance structure, which we'll talk about in a later video. So if we've gone over resonance structures at this point, then you can go back and say, oh look, this is a resonance structure too. There's 2 places where that double bond can go. All right, BH3. Let's take a look at this one. Boron starts out with 3 valence electrons, and each hydrogen has 1, so that's 6 electrons total. I'm going to put my least electronegative element that isn't hydrogen in the center, and then I'm going to connect with a single bond. Give everyone an octet. Hydrogen only takes 2, so it's good. Then I'm going to stop and count. How much have I used up? I've used up all of them. There's none left for boron in the middle. And excuse me, we know that boron is perfectly happy having less than an octet because it's one of our 2 atoms that are, to the left of carbon. So this is going to be the final structure of BH3. It just looks like that. All right, I'm going to go over to a clean slide here. Okay. So PF5, let's take a look at PF5. So phosphorus has 5, I'm doing this one, it's got 5 valence electrons, and then you've got 5 fluorines. So we've got 40 electrons total. You put your least electronegative element in the middle, you attach everything else with single bonds. Notice I'm always doing the same steps, right? I always use those same 5 steps to doing a Lewis dot structure. Okay. Now I'm going to give my outer ones an octet. So I'm going to give all my fluorines an octet. Boom, 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 boom. Okay. And then I'm going to stop and count. So I've used up all 40 electrons. There's none left to go on my phosphorus in the middle. So I am all good. There we go. Okay. So the next one, xenon difluoride. So you want to stop and count up the electrons. And xenon difluoride, let's do this right here in the space below. Xenon starts with 8, and then you've got 2 fluorines there. So 8 plus 7 plus 7, that's 22 electrons. Hopefully I'm doing my mental math well here. Okay, and then I put my least electronegative element in the middle, and I put fluorines on the outside. And remember, the electronegativity of xenons are typically undefined, so we don't usually think of it as having electronegativity value. So you might be wondering, why did I put xenon in the middle, not fluorine? Well, we also know by definition that fluorine is the most electronegative element that exists. So fluorine's never going to go in the middle. It's always going to go on the outside, because it's the most electronegative element there is. All right, so xenon's in the middle, fluorine's on the outside. I'm going to give my fluorines an octet. Okay, and then I'm going to stop and count and say, how many electrons have I used up? So I've used up 8 plus 8. I've used up 16 electrons. So I've got 6 electrons left over. And I'm going to put those 6 electrons on the central xenon. And notice how I did them in pairs. So this is an octet exception, because notice how our xenon has 2, 4, 6, 8, 10 electrons around it. Same thing over here. Your phosphorus has 2, 4, 6, 8, 10 electrons around it in your final structure. Okay. And then we've got one more. So I'm going to go over to a fresh page. So ICl4 with a 1 minus charge. That's an ion. And we're going to look, this is iodine, and then 4 chlorines. So iodine has 7. Your 4 chlorines reach 7. So that adds up to, we've got 5 times 7, we've got 35, right? Plus we have an extra electron because it's got a negative charge. So you have 36 electrons. Did I add that up right? Okay. 5 times, yes. Okay, so we got 36 electrons. I'm going to put my least electronegative atom in the middle. That's iodine. I'm going to attach all my chlorines to it. Okay, and then I'm going to give my outer ones an octet. And notice how the more you practice this, the faster you will get at this process, right? So you just want to keep practicing these Lewis dot structures, keep going through those 5 steps until it just becomes second nature and you can do it really quickly. Okay, so now I'm going to stop and I'm going to count my electrons. So I have, I've used up 32 electrons, 8, 8, 8, and 8, that's up to 32. I've got 4 left over. So what am I going to do with those leftover ones? I'm going to put them on the central atom, even if doing so results in more than an octet. So notice how this is an octet exception, because the iodine has 2, 4, 6, 8, 10, 12 electrons around it. But I know that's okay because iodine is in row 5 of the periodic table. And we can have expanded octets in elements in row 3 or below. So if you ever end up drawing one of these structures and you find an expanded octet on an atom like nitrogen or oxygen, then you should say, whoops, I must have goofed, because only elements in row 3 and below can have an expanded octet. So it's always good to double check at the end, you know, that your element with more than 8 is actually in row 3 or below. If it's not, then you may have made a mistake somewhere else along the way. All right, so I hope that this helps. Let me know if you have questions.